As artificial intelligence is increasingly being used in high-stakes decisions, we have recognized the need for explanations. But what makes a good quality explanation, and how do we evaluate the quality of an explanation? Hello, everyone, and thanks for joining us. My name is El-Sharif, and I'm a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Jonathan Dodge. Jonathan is a PhD candidate at Oregon State University in Corvallis, Oregon, where he is being advised by Dr. Margaret Brunette. His research interests have varied, but he is currently focused on explainable AI problems in both the human side and the system side. Before returning to Oregon State University as a PhD student, he obtained his Master's of Science in 2009 in graphics from the graphics department, where he was advised by Dr. Ron Mature. His thesis project focused on understanding and supporting the needs for exercise prescribers and creating rich media to support their patients. Jonathan will be presenting his work, We Can Measure Explainable AI Explanations Better with Templates. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. So without further ado, I will now turn over the presentation to Jonathan. Please take it away.
Thank you. Hi, I'm Jonathan Dodge. I'd like to start by thanking my hosts for inviting me to present and the audience for listening. This talk is primarily based on the workshop paper cited here, though I will discuss experience from a couple of other studies along the way. So explanations for AI decisions have a wide variety of use cases, but in all of them, high quality is desirable. But what does that really mean? When conducting XAI evaluations, for what evidence should we be looking? Based on research from psychologists, they define two contrasting kinds of measures. As I share them, pay particular attention to three aspects of the evaluation, which will be highlighted in yellow. Specifically, the important distinctions are in the context, actor, and timing of the evaluations. Explanation goodness is defined in this way. One can make an a priori or decontextualized judgment as to whether or not an explanation is good. Ideally, the researchers who complete the evaluation would not be the ones who created the system under study. And now, let's contrast with the definition for explanation satisfaction, which is not the same as satisfaction in the conversational sense. While an explanation might be deemed good, it may at the same time not be adequate or satisfying to users in context. Satisfaction is defined as the degree to which users feel that they understand the AI system or process being explained to them. Compared to goodness, satisfaction is a contextualized, a posteriori judgment of explanations. Now that we've seen both definitions, let's recap the three aspects. Context. Satisfaction is defined relative to a task, while goodness is not. Actor. Satisfaction is measured from the perspective of a user, while goodness is from the perspective of researchers. And timing. Satisfaction is task relative, so it must be measured after task completion, while goodness can be measured anytime. Okay, so now everyone knows both definitions and how they contrast quite well. We claim that most research focuses on explanation satisfaction. The argumentation of this presentation proceeds as follows. First, while it may seem obvious how to design a study to measure explanation satisfaction, it is hard because humans are a noisy data source. Second, lab studies have limited duration, so participants do not experience very many instances of explanation. Last, goodness techniques allow us to consider multiple explanation instances at once, offering greater scalability. One approach for considering multiple instances at once is to think of explanations as being generated by a template. Templates are abstractions to simplify understanding the entire space of explanations, which could possibly arise. The earliest example of explanation templates I could find is from the planning community, using them for MDPs, and we see an example here. Templates are populated at runtime, and they're intended to avoid the complication of incorporating natural language generation into your explanations. It's a classic factory design pattern, where the template is the factory generating many explanation instances. Accordingly, rather than inspect each instance for quality, maybe we can just inspect the factory itself. So here are some more examples from templates from prior work by Binns et al., appearing in XAI. To generate the values they fill in on the template, they use the Wizard of Oz process, which in this context means the values we see here are just made up. However, they followed a rigorous design process to construct the template itself. Upon reading the paper, I thought I could probably programmatically generate something like this, and so I did. And we'll go through the ones I created later, but I'd like to quickly go over Binns' version from the car insurance quote domain. On the left is input influence explanation. It intends to show the sign and magnitude of each feature's contribution to the prediction. On the right is demographic explanation. It describes the distribution of the training data. And here are the other two examples, templates from Binns. On the left is case-based explanation, characterizing something in the training set that is similar to the input. So here we see this user as being compared to this Claire person. And on the right is sensitivity-based explanation, which describes the changes one could make to the input to elicit a different prediction. Building on Binns templates, I created these for my work in the recidivism prediction domain. These are two example explanations provided by the system used in my previous work. The black text is static, and the added red highlights show text based on calculations about the input. This is intended to show you how explanation templates get filled in. If you're familiar, it's kind of like a Mad Lib, with parts varying and parts fixed. At this point, I'd like to highlight the idea that satisfaction and goodness approaches can be used in tandem. So let's see how we might do that by discussing some of my previous work in which we investigated explanations. So here's an example of a study using satisfaction measures from our lab. It uses a simple domain that we call 4 towers. The agent controls the white tank in the middle of the board and chooses to attack any of the 4 quadrants. If the tank survives, it respawns with the same health at the middle of a new board with a variety of friendly or enemy objects. I don't want to get much deeper into the details, but the important points are twofold. First, the state space is pretty big. This is because each object spawns with random amounts of health. There are several different kinds of objects, and their positions are random. Second, the action space is tightly constrained. There are just 4 options. Among the participants' tasks were to predict the action that the agent would choose. And this is how they did at predicting those actions. Data here is sliced per treatment, varying explanation style, given by the colors of the bars, and per decision, given by each bar cluster. Note that no explanation style consistently outperforms the others, partially due to floor and ceiling effects. To illustrate ceiling effects, consider DP5, where everyone predicted the agent's action nearly perfectly, even those with no explanation at all. Conversely, consider DP10, where all participants averaged worse than a random guess. Here, random guessing would yield 25% accuracy because there were only 4 actions. To illustrate variability in explanation consumers, consider a scientist describing a complex phenomenon like quantum computing or AI. First, imagine they explain it to another scientist. Then imagine they give that same explanation to a child. The explanation itself could be of high quality. It just may not be appropriate for some audiences at some times. Added to the variability in consumers is variability in the state action space of the domain where the AI is being deployed. With very large action spaces, the probability of a correct participant prediction of the AI's behavior can become vanishingly small. Meanwhile, consider that in-lab user studies are typically designed to be executed within a 2-hour window. As a result, the amount of participant exposure to the system is actually quite low. As an example, in this study, we showed 14 decision points to participants over the available 2 hours and observed no learning effect. A learning effect might be expected, as the participant is exposed to more decisions and more explanations, and their understanding grows. This means we might expect to see an increasing trend line like the red one shown here, but we do not. The variability described in the last slide, when combined with limited exposure, results in participants who are essentially gazing into a vast expanse of behavior through a tiny peephole. Now, for another example of a satisfaction, which I will cover in a little more detail, I'd like to start by going over a high-level view of what we did to study these explanations. As I go through this figure, don't worry too much about how each piece works. Instead, focus on how they connect. So we started with some data, which might have some bias present. To reduce the bias, we use a debiasing technique, which runs as a pre-process and transforms the data. So now we have two data sets, which are similar but not the same. We then trained two classifiers based on each data set, which we'll call raw and processed, which again are similar but not the same. Next, we programmatically generated 4 types of explanations, denoted by the 4 colors of arrows for each test sample, of which there are around 1,000. Remember, we were interested in human perception, and 4,000 explanations is too many to do a survey with, so we needed to choose a smaller set of samples. Last, we ran a survey to measure how humans perceive decisions from the classifiers. Participants rated agreement with the prompt shown here, how the software made the prediction was fair. So now we understand the end-to-end plan. Let's make the important pieces more concrete, starting with the use case. Decision support software is used in courtrooms today to inform sentencing and bail. In DSS settings, the human is providing the final decision, but among the data available is ML output, which is potentially biased. Note that these systems are based on proprietary methods and data, but we were able to build our own kind of similar system based on data from a watchdog group, ProPublica. Here I'll skip to step 3 because this talk isn't really about debiasing or making classifiers. Now, armed with a classifier, we programmatically generated textual explanations based on templates from recent work. We studied the explanation factor because it's the interface for a human in the loop to scrutinize the model. And we were interested to know if some explanations reveal model fairness better than others. So now let's meet our contenders. First, we have input influence explanations, which are global, meaning they will generate the same or similar explanations for all inputs. The input influence-based explanation describes the impact the various features values will have on the decision. The boldface lines highlight the categories containing the feature values for the individual for which the explanation was generated. Now, to read an individual feature line, let's jump down to the prior convictions feature. As one might expect, if a defendant has more than 10 prior convictions, it is positive evidence that they may reoffend, which is indicated by the plus sign. The fact that it is strong positive evidence is indicated by the large number of plus signs. Conversely, if a defendant has no prior convictions, we might expect that to be strong negative evidence that they may reoffend. And we see that as the case with a large number of negative signs. Now, if a feature has a coefficient of 0, it means its impact on the decision is slim to none. Participants only saw one type of explanation, but I wanted to show a side-by-side to illustrate the effect of preprocessing. So here we can see the effect of the debiasing step, where in the preprocessed classifier, both races have a 0. Last, by visual scan, we can see the classifiers are similar. The strings are of roughly equal length, there are no big sign changes, things like this. Second, we have demographic-based explanations, which are also global. They describe how the training data is distributed. Again, we can see the effect of the debiasing step in the preprocessed data classifier. Further, we can see that with a visual scan, the data has moved around, but not by a very large amount. Here, consider that while I've shown you very few instances of these explanations, they follow a consistent template, and so you know what the others will look like. Third, sensitivity-based explanations, which modify the individual's features one at a time and see if the decision changes. If it does, we report a line like the one highlighted, This defendant has juvenile priors. However, if they had not had those juvenile priors, the decision would have changed. Note that each individual will have different sensitivities, so this explanation type is local. In our local explanations, the filled-in variables are in bold, while the rest of the explanation uses regular font. Case-based explanations are also local. Here we depart from the BINS template. Their approach was to do one nearest neighbor search. In our case, the feature space was small compared to the size of the dataset, so we were often able to find exact feature matches. If matches are found, we report on the distribution of their labels. Otherwise, we fall back on one nearest neighbor search. Okay, so now we're here in the diagram, with too many explanations, needing to choose a subset to study in our survey. Here, I'd like to pause and highlight how few of the explanation instances available in the test set ended up as part of the experiment. This illustrates my point earlier about how little exposure to this system can be granted in most satisfaction studies. For 1,000, it just became 100. Finally, we're ready to combine our ingredients and run a survey. In that paper, we reported on our participants' answers to the agreement with the statement, how the software made the prediction was fair. We conducted the survey with Amazon Mechanical Turk crowd workers, and we asked them some important individual difference factors, but the one I'll focus on for the purposes of this talk is trust in ML. Each saw 6 decisions, which I'd like to pause again and highlight. 6. This is after 4,000 became 100 for the set of all decisions that any participant would see. One person is seeing 6. So before I show you the kinds of insights one can gain from a satisfaction-oriented study, I'd like to zoom out for a moment. Satisfaction results are a very precise measurement of the quality of a very small set of design decisions and explanation. Namely, in this case, which of these 4 explanation templates the explanation followed. But to get there, we made many more design decisions than were able to be compared with a single satisfaction study. So how did we validate those? I later realized that internally, we had done many iterations of informal goodness measures. To clarify, during research meetings where I showed preliminary output, various stakeholders would discuss, request changes, whiteboard things out, stuff like that. So here's the flavor of the kind of results satisfaction studies can yield. Participants with high trust in ML rated decisions as more fair. This effect was stronger when they were given a global explanation, which is highlighted in purple. This illustrates the importance of understanding the right individual differences when designing and choosing explanations. To clarify some of the described issues, consider the following geometric interpretation. In the figure, positive examples are marked with a blue plus, while the negative examples are marked with a red minus. The decision boundary is the thick black line. Now, suppose a user requests an explanation for an instance at either of the 2 question marks. Input influence-based explanations attempt to expose feature coefficients, and thus describe the decision boundary itself. Demographic explanations instead describe the distribution of the training data, in other words, where the pluses and minuses are positioned. Note that this does not change per sample, and is thus global, meaning both points will get the same explanation, up to highlighting. On the other hand, local explanations will change given different individuals. Sensitivity-based explanations vary features, one at a time, checking to see if the decision changes. Geometrically, this is like projecting an axis-aligned line from the point until it collides with the decision boundary. Each individual will have different sensitivities. For example, we might expect the question mark near the boundary to have many sensitivities, as small changes might push it over to the other side. Conversely, the question mark far from the boundary may have a small, or possibly empty, set of sensitivities. Case-based explanation is also local, and it corresponds to expanding a sphere around an input and reporting on the distribution of its contents. Consider that a sphere around a question mark near the decision boundary is more likely to contain examples of the opposite label than the question mark that is further away. So before the detour, we were here with these 2 examples. which illustrate what we were just discussing geometrically. From these two examples, it is evident that satisfaction results can vary based on the input. That is to say, the top explanation is far less convincing because the data highlighted in blue supports a different classification. Thus, we describe this kind of explanation as self-refuting. Now, we've added the red arrows to the figure, showing where the calculated values fall within their distribution, shown on the right in blue. Depending where these values fall, satisfaction results will vary. Further, participants only typically work with a small number of explanation instances, and self-refuting ones are quite rare. Thus, they may not observe enough explanations to ever see that the template can generate self-refuting explanations. However, note that the explanation template is the same in both cases, only the input changed. So here we compare the design we used, which is on the top, to a strawman explanation template that is known to be bad. The intent of this exercise is to explore the extent of our ability to characterize how bad it is. So the advantage of this alternative proposal is that it will not refute itself. But that advantage came at a cost. According to known taxonomies, completeness decreased, and this is because it's telling less of the whole truth. So did the overall goodness go up or down? We would think that most would argue down. We can't really measure how much. And this exposes a critical weakness in the goodness approach. The vocabulary and calculus currently available to us cannot adequately describe and measure the implications of a single design decision. Thus far, we've mostly restricted the discussion to textual explanations, with a kind of a Mad Lib form. However, now I'd like to broaden the idea of templates to visual explanations using a search tree. So here, we imagine the agent can plan with a model. So given a state and an action, it can predict a future state, and possibly search again from there. At this point, I'd like to observe the following. As the state action space grows, so does the explanation space. And by that, here I refer to the space of trees that the agent could possibly produce as a visual explanation. This means several things. First, the agent cannot fully search the state action space. As a result, we need to be prepared to explain actions that were potentially fully considered, pruned after triage, or never searched at all. Second, satisfaction increasingly will not cover the explanation space. As a result, I think we will rely heavily on goodness approaches to evaluate explanations sampled from large state action spaces. Last, humans will be decreasingly able to fathom any of these spaces. As a result, we use HCI techniques like iterative revealing. But in order to do so, first we need to define and then find important substructures. As an example, in some other work out of our lab, we focus on what is known as the principal variation, which I like to think of as the sequence of states that arise when assuming optimal play from all sides. To conclude, we suspect many XAI design decisions are never assessed unless the designers use goodness, strictly due to the impracticality of doing satisfaction studies at the scale needed for full coverage. This leads us to the core hypothesis of this work. Studying one or a few explanations is well suited to explanation satisfaction-oriented methods, but the template level may require explanation goodness methods. In a sense, explanation is a user interface, and interface designers have long used a wide variety of techniques related to goodness, such as design guidelines, cognitive dimensions, cognitive walkthroughs, things like this. And we feel that improvements in the rigor and measurability of goodness mechanisms will bring outsized benefits to XAI designers and researchers as compared to improvements in satisfaction. Thank you for your attention.
Can you hear me?
I can.
Yes. So thank you, Jonathan, for that excellent presentation. We will now start the Q&A part of the session. And we will be presenting John with live questions as well as questions we have received in advance. So maybe the first question that I will ask Jonathan is, let's take a typical machine learning practitioner shop that is using some of the standard tools we have, like SHAP or LIME, and they're generating local or global explanations, and they're doing uh, uh, haphazardly, if you will. I mean, they're running the post hoc explanatory method, and they're getting feature importance outputs as their explanations. What would you recommend as their first step on their journey to being more systematic and more rigorous in generating explanations?
Okay. Well, maybe I have a slide to prepare on this one.
Okay.
So I think there's kind of it's a tricky business. The first thing I would say is you should recognize that you're probably manipulating templates whenever you're doing your whiteboarding and things like that. And so thinking about it more systematically in that sense is a good place to start. Another place I would suggest starting is read some papers like the ones I have on the screen now, or things that cite these papers. One of the things you'll find is that these are more systematic. So this thought that we have guidelines coming, they're being improved, kind of keep your ear to the ground in that way. And what you'll find is that when you're doing your whiteboarding, your ability to estimate the goodness of something is going to get better.
Okay. Now many of the concepts, or at least this work, is really at the intersection between human-computer interaction and machine learning. I assume that would it be a fair statement to say that many of the concepts and many of the methods that you're discussed are available or used in other domains that don't involve machine learning? I mean, we've got explanations for any system that's generating an output that may or may not necessarily include machine learning.
I agree with that characterization, and I'll say the Hoffman paper that I cited much earlier, where I pulled the goodness and satisfaction measure definitions out of, a lot of the research about explanation coming from the psychologists are looking at just sort of general automation or human interaction with other humans and things like this. So a lot of those principles are more tried and true than we might lead ourselves to believe. And I also think this is very highly disciplinary. Highly interdisciplinary business. Personally, I've thrown some citations to philosophy of science, and some of our recent work is looking into visual search of baggage handlers and things like this. So the more strings one can weave into their work, the better, I think.
Okay, which I suppose leads me to my next question: is are there unique challenges to the maybe AI community that that maybe we have that we're starting to run into, or there's something different about decision support systems that are supported by AI that just that warrant their own challenges or their own approach?
So that is a very deep question. The short answer, I would say, is one of the things you find in the DSS setting in particular is they don't go with the fanciest, most accurate models. Deep learning is not preferred there because what they really want is to be able to reason about the output. What they don't care about is like whether or not the output is actually correct. And so what you'll see there are a lot of things like logistic regression, models that are not going to have as high of an accuracy, but the output is easy to reason about. So that's the sort of thing that you'll often see there.
Okay.
To kind of tackle it on a different level, I would say that the complexity associated with AI systems is so much higher than a lot of the automation examples that people were looking at earlier, right? If you're building an actual factory that's outputting widgets, you can look at the widget conveyor belt and think about it in that way. But we have so many more learned components, especially now that stuff coming out of DeepMind, for example, their AlphaStar agent, it's multiple learned components combining their forces to do things. And so, now we've got extra layers of not only is this neural network working, is the combination of neural networks working. So there's a lot of challenges there. So that's why I say it's kind of a deep question, and I'm sure even that answer has only scratched the surface.
And I suppose, I mean, you've alluded to the fact that we, as human beings, have a cognitive budget where an explanation really cannot exceed a certain space, if you will. Otherwise, it's going to be useless. So, are we almost at a point where we just have to accept that there are some AI solutions out there that are just beyond our ability to understand them, and maybe the best we can do is a very high level summary of what is happening, and at best that's an estimate or an approximation?
It's a good question. I feel that there's with a system of any, as complexity gets too high, it sort of becomes matters of belief in a way. And so I think that's kind of what you're alluding to. But I, at least from the HCI side, one of the things that I think is quite challenging is, we can easily think about, well, if I could somehow get everything on the screen, maybe people can figure it out. But the reality is you can't even get it on the screen. And so you have to think about, pruning not only at the agent level, but also potentially at the user interface level. And so it becomes a little bit of a challenge, I guess. So I don't know if that answered the question well, but
no, you did. Thank you so much. Now, you've highlighted the fact that really okay, so explanations, let me just go back to my notes here. We should be thinking, in terms of satisfaction versus goodness here. Could you just help us and just maybe or re-highlight the difference between those two concepts?
Okay, so my really short TLDR, satisfaction is basically, does it help somebody do a thing?
Okay.
And then goodness is more like, does the expert panel think it's good? And so the analogy I'd like to draw here is, you can imagine figure skating in the Olympics, for example. Somebody does their routine, a bunch of people hold up the sign, you see a 9, and you realize that's good, right? But you as the audience, it didn't help you do anything. You're just viewing what they judged it to be.
Okay. And are we taking any steps closer to having numeric or quantitative measures of those two terms, satisfaction versus goodness? I mean, are we taking steps, or are we getting to the point where we could actually design studies where we can have a satisfaction score, a goodness score, and anything beyond a certain number is good and below a certain number is bad?
That's a good question. I feel so satisfaction you can likely quantify very easily, because usually these are coming out of a Likert score or something. So you can look at your means and other parts of your distribution to gain some insight there. I think quantifying goodness is going to prove more challenging. So towards the conclusion there, you might have noticed I drew some analogies to other things coming out of general user interface measurement. And what you'll find there is that there's a lot of kind of rigorous processes one can follow. There's, assistive techniques, things like this, but they still aren't really going to say, this interface is a 20 and this interface is a 30. The caveat that I would put into this is, if you look in, I don't remember when this was published in IUI, but they recently gave the author a lifetime achievement award or whatever for this paper's impact. But there's a technique where essentially what you can do, if what they were doing was laying out a user interface, right? So you maybe you have to put 3 buttons and a slider, and so you arrange them, and then you arrange them again, and you show them to designers and say, which do you like better, A or B? And they say A. And after you aggregate enough of this information, you can kind of infer a function of what it is that actually makes a better layout. But even in that context, I think what you're kind of doing is aggregating an implicit function embedded in the human across a bunch of people, and then you're embedding it in an implicit function in the system. And yeah, it's going to be spitting out numbers, but they're not based on the actual goodness measures as we might want them to be. They're sort of as someone decided to operationalize them and then aggregate across the population.
Okay. Now, thank you for that explanation, Jonathan. And now I do see you have a broad range of explanation techniques, case-based reasoning, sensitivity, influence function, demographic, etc. So would it be safe to assume that we are better off diversifying or having multiple explanations collaborate together and maybe giving the user the option to examine that explanation through different modalities, if you will, or different methods?
I think so. When we were designing the study, there was some discussion about investigating some kind of hybrid, right, where we could have one treatment be, input influence and through the others, right? But then we could have another treatment be input influence, like a global plus a local or something like that. Because at least personally, as I was developing it, I had my massive quantity of output, right? And it was just all of it, right? And so it was helpful to me, at least, to see the things juxtaposed next to each other. And so I think that's probably the right intuition. I will say, though, that of the four styles that I presented, even though this presentation kind of focused on the case-based explanation for the purpose of like holding up straw man and stuff because it's easy to understand, I think case-based explanation is generally a very bad idea. And part of the reason I say this is, so first of all, BINS, when they researched the case-based explanation, they found it to be the least preferred. We also found that. And then also it has these issues that you kind of saw where that self-refuting explanation, the reason that's happening is because it's not sound. The classifier isn't a k-means cluster or something, right? And so when your explanation is kind of assuming that kind of a structure to the classifier, you're lying to people, right? So.
Yeah, you just shocked me, by the way. I always thought that case-based explanations were more intuitive, and there was a little bit that they presented something logical.
Yeah, I can say a little more about that, perhaps. So let's go back to my geometric interpretation. So one of the things I'll note here is that similar things are similar up until the point where they're not, right? So, so it's kind of like, the whole notion of case-based reasoning is all about, your metric of similarity is going to give you a good result. And it will when you're over on the, this question mark. But, as you kind of move closer and closer to the decision boundary, it's going to do worse and worse things to you.
So really, case-based explanations, I mean, I think your argument here is they're useful when they're in a tightly defined cluster, if you will, of the data.
Yes.
And when that does not exist, don't force it.
I think that's a correct characterization. If the internal classifier is a clustering-based kind of thing, then yeah, the right thing to do is to use a case-based kind of explanation. But otherwise, I generally think it's quite poor.
Okay, so what would be the best explanation based on the options that you presented to us?
Well, so for this particular domain, because again, we're kind of living in this decision support domain where we prefer things like logistic regression with linear decision boundaries and simplicity and things like that. My personal preference is the input influence-based explanation. I think it tells you the most about the feature space because it sort of here's where the decision boundary is. But that breaks down when you've got a nonlinear decision boundary being encoded by a deep network or some Gaussian kernels or whatever it is you're doing. So I think that what's important is not so much the using of the kind of quote unquote best technique. It's more the match between the technique being used to explain and the techniques being used to actually do the classification.
Got it. And hence, going back to we're better off having a portfolio or a variety of explanations, and some of them are going to be a better fit in this context, and some of them are going to be a better fit in that context. And okay, so would it make sense then to predefine criteria of fitness that this explanation, in order for it to be useful, these are the preconditions that need to be satisfied, and if we can identify, and then maybe have some mechanism of identifying the best explanation for a particular use case or a particular instance.
Yeah, I think that's kind of the spirit behind the citation I just had up a little bit ago. Let me dig that up again.
Okay.
The Standing Wang paper, that's kind of their general approach. Is what they want is to kind of build a nice flow chart. The one they have is quite sparse still because, again, this is all very new and we don't really know what the hell we're doing yet. But soon we might, and that's kind of as we fill that in. I think it might be a little bit pie in the sky because I feel it's kind of going to be one of those things where whatever taxonomy we've encoded in that flowchart is going to be a little bit stale, right? It's going to be kind of based on last year's techniques and taxonomies and stuff. But over time, I think we'll get to a better regime there in terms of if you think of the world as I don't know if you're familiar with Thomas Kuhn's structure of scientific revolution, but I think right now we're in a revolution phase in AI, and once the landscape kind of settles a little bit, we can all agree on some terminology, and these tools will probably be a lot more useful.
Okay, excellent. Now, Jonathan, before we wrap this up, are there any final thoughts that you would like to share with us?
Not really. I think the main thing that I would want to say is, if you're a researcher, think carefully about goodness and what you might be able to contribute or, use it for. And if you're a practitioner, then I would suggest kind of keeping your ear to the ground in kind of HCI communities and be a little more interdisciplinary, I guess would be my main takeaway.
And that's a really important message, Jonathan. I thank you for a great presentation and thank all of you who joined us online. To see more free content like this, please visit our website at ai.science and log in to access slides from this and other sessions. Also, make sure to subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. This concludes our event. Thank you for watching.